Hello everybody present here and also watching us online. Today we will continue with our session of seminars in physics at the doctoral studies at the University of RIJEKA. Today two last seminars will be presented in the field of condensed matter physics. Our first speaker is Josip Jakovac. His mentor is and Josip will speak about the fundamentals of density, functional theory and its application to 2D materials. Just before Josip starts, one comment. I heard from those watching us online that it was very good that they could understand, see and hear the speakers. However, that the audience was often too quiet. It's because we have here in this camera the microphone. So during the discussion I would kindly ask all of you who have questions to come here closer to the camera to ask the questions, if you don't mind to stand up, so that also our remote audience can follow the discussions. Thank you, and Josip, please, you can start with your presentation.
Thank you. Hello everyone. As Professor Prester said, my name is Josip Jakovac, and I will talk to you today about fundamental of density functional theory and its application to the measurable materials. What I will talk about today is some introduction. We'll say some general terms about density functional theory and the motivation that propelled me to give this seminar. After that, I will show in brief methods of solving the many-body Schrödinger equation using density functional theory, and then I will describe some terms important for DFT application to crystalline solids, and we'll talk something about Levy density function theory. And then at the end of this seminar, I will show an input file for my calculations for doctoral thesis, and we'll explain some important lies that define the calculation itself. So, density functional theory. It's ab initio calculation. It means in Latin from the beginning. That means that it only uses quantum mechanics to give results. There are no empirical parameters needed from the outside. Actually, all it needs is Coulomb interactions between all the electrons and nuclei, Fermi statistics, and the Pauli exclusion principle. Results, of course, goals we seek from DFT is to describe properties of matter, in my case, the measure of crystalline materials. And although not that objective, very important for me is to make the theoretical and experimental solid-state physicists feel closer to each other, because they know the reason. So, what's the problem? We should find the ground energy state for a collection of atoms by solving the Schrödinger equation. So imagine a bunch of atoms in some kind of crystalline solids, oscillating here and there, moving left, right. Its atom density is shifting left, right, and this is a Hamiltonian in rough how we might show it. Hamiltonian operator. Wave function depends about electrons positions and nuclei positions. A general Hamiltonian, of course, consists of kinetic energy operator, potential energy operator. Kinetic energy operator is a general kinetic energy operator, so it means it should describe all the particles moving around. And Coulomb operator is of course of this form, and Qi and Q J are all of charged particles in the story. in this our story. So, at least to me, it seems a bit too complicated to calculate. There are a bit too many factors to track. So what we do? We'll try to apply Bohr-Oppenheimer approximation here. Basic idea of it is that mass of the nuclei, the big R, is much bigger than the mass of the electrons. So we can approximate that atomic nuclei are actually frozen. So that's the reason why we might that dynamics of atomic nuclei and electrons they can be separated in this manner. So this way, wave function of nuclei depends on the position of it is static, while we just try to find the ground state for electron wave functions. They depend of course on electron positions. Here is the eigenvalue equation, and here is the Hamiltonian. It looks now much better when we got rid of those pesky nuclei. But there's always but. As I said, we would like to solve those Schrödinger equations for all the electrons separately. This is separable kinetic energy part of the Hamiltonian. This is external potential from nuclei to the electron, but this is the interacting electron-electron term. And the problem here is that this one is not separable. Seems pretty nasty, but also that's not it. When it starts. Right now, we have 3 times n, where n is number of electrons, equations, Schrödinger equations to solve. And depending on a system we solve, it can be it can use pretty amount of computer resources. So the solution of this thing is to define the electron density here, and this way we reduced those 3 n number of equations to 3 in x, y, and z equations of electron density. At the end, we shall try to solve Schrödinger equation this way. But let's get back to this Hamiltonian problem, the beginning. We'll call Hartree-Fock approximation to the rescue. So this is our Hamiltonian. The general idea is that the jth electron in the system is treated as a point charge in the field of all the other electrons. It's called a mean field approximation. This Hamiltonian, it looks like this one, except this one, it seems like it is a function of only one electron. Luckily, this one takes care of Pauli principle, as I mentioned at the beginning, that's very important here, while Hartree approximation doesn't. So this one is much better. And also this means that in this R vector, also spin should be included inside here, spin term. Luckily, this way, by this approximation, we can simplify the many electron problem to many one electron problems. And they propose this idea that many electron wave functions we can put like a product of n single electron wave functions. The problem here is, of course, that as they are separate, those electrons aren't correlated here. So the approximation issue here is that we have an eigenvalue equation where this Hamiltonian here is this one, but this wave function is an eigenvalue function of this Hamiltonian. So the problem is if we even manage to solve this one equation for one electron, it means that this orbital, this spin orbit, this electron should change to fit this equation. But it means, because of this mean field approximation, that all the other electrons should change, because mean field approximation of all the other electrons includes spin orbit of this electron, and just moves around. But luckily, for ground state, it can be approximated pretty nice this way. Spin thing is pretty important here. How tree has the lack of it. So now, what do we have here? Product of this wave function and this approximate Hamiltonian. As I mentioned earlier, this way we can define the electron density in terms of individual wave functions. Two is because of the spin degeneracy here, but they are now separated. And now comes the reason why we define this, except for easier calculation of this, because of two important theorems that actually are in the heart of density function theory. The first one says that the ground state energy E is a unique functional of the electron density. It's here. So it means that we can define the energy functional only using this electron density that we defined before. And the second one says that the electron density that minimizes the energy of the overall functional is the through ground state's electron density. So if we find the minimal of this function, then we get the through ground state electron density here for a whole system. This functional, energy functional, looks like this. Here is that N R, electron density included already here, kinetic part, nuclei potential part, correlation part, nuclei part, and the one part that somehow got here, but we don't know nothing about it. It's exchange correlation energy, and it is actually it is approximated by exchange correlation functional, and it consists all the quantum mechanics terms. Luckily, we got using the Hartree-Fock approximation somehow this exchange part, but correlation function, correlation part, we should approximate somehow different. But everything is in this energy. As I said, it needs to be approximated, and it can most easiest ways are using the local density approximation and general gradient approximation here. So now when we got our theorems and we got our charge density here, we can move now to solving a real Schrödinger equation. We will use a sham method here. It is a simple calculation. It finds a ground state energy density, and it solves a set of single electron wave equations that only depends on electron density here. This is in rough the form of the Hamiltonian, as I explained the energy before, and this is its ground energy we'll get later. So these are the single electron wave functions. There we did that Hartree-Fock approximation as a form. Now what's the procedure? We get some random trial electron density here, and we solve those n constant equations using this electron density, and we get those single electron wave functions this way. Yeah, that's it. After that, we need to calculate the other electron density based on these calculations we got here using this formula. Here should be this mark, what to write. And after that, we need to compare. If the two don't fit and not equal, then we should repeat from step 2 using this other result in here with this one goes here. And if it fits, then we found the true electron density obtained. The problem with this method is that sometimes, and I experienced that case, it doesn't find the real minimum, the real ground energy. Sometimes it can miss the smaller ground energy and find something else, but usually it works fine. When I worked with my mentor, on occasion, it found the wrong ground energy. And this is the first part of my seminar where I explained those equations. And now I shall move to explain some terms of DFT in real materials. So, in free space, we have a free electron wave functions. It is a plane wave. We describe it as a plane wave. Inside ionic potential, we have a Bloch theorem here that says that one electron wave function inside a periodic potential is a product of a plane wave and a periodic function with the same period as the potential here. This is the equation, and this is the equation that defines that space. This Bloch theorem will be applied here. So this is the plane wave. It's one dimension show, and this is the potential. As Bloch theorem says, this is the total wave function of electron in ionic potential. So as I mentioned, we use this in K-space, and we use Fourier transform to do a transformation from the real space to the reciprocal momentum space. Why we needed to remind us to the Bloch theorem is to define the cutoff energy. One really important thing here. Let's mention another theorem, a Fourier theorem. It says that every periodic function can be written as a sum of all the complex exponential functions that share the same period. So we did it here, and we wrote this potential function this way using complex exponential functions, and they say the same period, this g vector, and if you recall this g vector in K-space, we defined already here, so this one becomes G. Now, as this is a infinite sum, each plane wave in this sum has kinetic energy of this form. Now, the problem is, as if we go on and on and on and on, this kinetic energy also grows to infinity. So we should cut it off somewhere, and that is why it's called a cutoff energy. That is where we set where the sum starts, and we choose wave functions we shall observe in our calculations. We don't want them to go to infinity. Now let's say about one more thing. It's called K-point sampling. So this is the primitive. This is the primitive. Excuse me. This is the. This is the primitive lattice, and this one is the first brilliant zone. It is actually the primitive weakness side cell in real space, simple space. This is here, and this is a term for k vectors to be included here. As we set those vectors that span this space, already using those equation explained before, but as in quantum express calculations, we do not have real borders of the specimen to look so. We have to span somehow k vectors along here, along this first brilliant zone, and we do this by k-point sampling. We have to put it artificially because the specimen we observe here has no borders. And there is another important thing here. It's called pseudopotentials. In materials, we observe here only for most of its properties and everything, only valence electrons matters. So why wouldn't we consider to replace the electron density from a chosen set of core electrons with a smoothed density? It's called a Fourier approximation. This way, we have those inner electrons together with the core embedded together into these pseudopotentials, and then this way we can only deal with outside electrons that are important to us. And those pseudopotentials, they can construct. There is a method to construct, but of course, library is available online. So if you want to calculate something, you don't have to construct your own pseudopotentials. And at the end, let's look at the input file. Okay, we can see something. Let's look at the input file for my calculations I shall embed into my doctoral thesis. So this is a self-hypothesis calculation. It means that in this calculation, we shall search for an electron density, the result using Kongshamn equations. What does it mean? Calculation SCF, it means it's self-consistent calculating. We start mode from scratch. It means that if this calculation somehow stops for any of the reasons, we go from the beginning. Maybe sometimes if there are bigger calculations, maybe it might be a good idea to proceed where we stopped, but sometimes they can, sometimes when we go from the beginning, things can go terribly wrong, so I prefer this. This is the prefix that describes the material here. Now there are some variables here that I don't get completely yet, but this one, pseudo directory, it describes where are those pseudo files I described earlier. Verbosity high, it describes about in the result, in the output file of these calculations, it describes what it will show, some additional information. So here we describe our system, calculator one. If we have 4, it means it describes a hexagonal lattice. These here are constants of our hexagonal lattice in angstroms. This number of the atoms and 9 kC8, and this is a number of different types of the atoms, gallium and the carbon. You may wonder if I am speaking about 2D materials, why is the C parameter so big? The reason is that quantum expression it does not return to the materials. So the reason here is to separate those two planes so much that quantum expression doesn't see any correlations between them, so that it sees like different things. This is the cutoff energy I mentioned before. It is in Rydbergs for this system. This is some smearing stuff, some not so clean and pure things, and this one defines that in all the symmetry we kill the inversion transformations. This is something regarding to the electrons. This is a diagonalization method. And here is the one important thing, convergence threshold. So when the calculation converges to the real result, this is the, this is the, wait a moment please. This is the toleration we can allow for calculation where it can end. So here we have atomic species, carbon and gallium. Here are atomic masses, and here are the pseudopotentials. I mean, these are the files here. Here we have atomic positions in odd form. It means those are fractional coordinates, and they depend about these constants here. So you may notice here that although we are in one two-dimensional plane, this K atom somehow got out of the plane. The reason is this, because this file is already relaxed. So what I did here, I did a relaxation of it. I found the minimum stress of the whole system, and that is why this gallium atom got so out of the plane. But later in calculations, actually in the procedure, I set some stuff and took care of this. Although this is also good thing to proceed with the non-self-consistent calculations. And this is what I mentioned, the K-mesh. Here it is 8 times 8 times 1. Why times 1? Because I'm doing it two-dimensional materials. So what I did, in those first Buon zone, I put 64 artificial K points here. That's just enough. First I tried with 10 times 10, well, put 100. But the thing is that after when I did non-self-consistent calculations, it took too much time to proceed with it. So I canceled it and used this one. And thank you. That's my seminar about instructional theory. Thank you.
Thank you. Can I get the sheet with your names, please? Thank you. To mark the questions. So now I would like to open the discussion. So far there have been no questions put online, and therefore I repeat, if somebody from the audience following us remotely has a question, please send me an email and I will check it now and ask the question as we did yesterday. And now let's start with the discussion. It was Antonio, Silvia, Željko, Virna, Zdravko?
Yes.
Okay, just a moment. Okay, so please, Antonio, can start. And come here. So everybody who asks a question can
speak loudly.
Please come here because here we have the microphone and also the camera. So I think for the remote audience, it's
So here's okay.
Come here. Don't be afraid. I don't bite. I just beat people with the sticks, but I don't bite. So
okay, I take his stick away and then.
come.
And
Okay.
here people can also see you and hear you. So I think it's much nicer.
Okay. So I have a question. So your last slide when you have had the stuff. So you said that you actually you do 2D calculations, but you still keep the C.
Yes, I said because this way any interaction is
It's
dissipates.
Yeah. Okay, I can get this, but still, I think does the calculation actually calculate the third dimension?
Yes, it does.
So that seems like a kind of a waste of resources.
Yeah, but I didn't find a way, at least till now, to pursue quantum espresso. Maybe Vast can do it or Rabinit. I didn't find a way to pursue quantum espresso to just to set exactly to the calculation plane, just to do calculation edit.
Yeah, okay. I mean, that's a good hack then, I guess.
I don't know for Rabinit or Vast, but as for this one, I didn't manage to.
Okay. And another question I had. So when you had the steps for DFT, some slides back, I don't remember which one exactly. Was it that one? Enough. Yeah, sure.
No, it starts here.
No, you had like a step where you mentioned that you have when you do the update of the density.
Update.
Yeah. Where you mentioned that you have that it overshoots sometimes.
It overshoots what?
Your solution, is it this one? It's hard to see from here. Yes, you mentioned. So you mentioned that you calculate you have your density.
Yes.
And then you update it by setting density equals to 2 times product.
It's here. It's here. Yeah, it's here. Yes.
Yeah. Okay. Okay. So. Anyways, what you said is that sometimes you update it and then it overshoots. It doesn't get to the minimal of energy.
No, it's here. It's here at the end. At the end here, I say that this consham shim this procedure. The thing is that when you see so and when you do this at the end.
Yeah.
So
you sometimes don't.
The thing is here that the second theorem, this one, that finds the minimum. It says that the electron density minimizes the energy of this electron density. The minimizes this functional.
Okay.
Sometimes it found the wrong one.
Okay.
And you said that you will.
have it.
No, that's recorder.
Sorry for
The thing here is that sometimes you find the wrong density in all this functional stuff, and try to minimize it in this way and find some minimum, but it is not the biggest one, it is the real one. So
it finds a local minimum.
Yeah, well, so it's a functional.
Yeah.
And it finds, okay, this one might be the smallest one, so let's minimize it here. Oh, this is a minimum, and it doesn't see the global one, says, I'll take this.
Yeah, so it kind of gets stuck at the local minimum.
Yeah.
I see. So what you do then you just restart the calculation and it finds
actually, computer should be a deterministic machine, but yes, what I do, I actually just restart a calculation, and then I just hope this time maybe you'll find the real.
I'm familiar with this kind of numerical problem.
In the deterministic machine. Yeah, it shouldn't be so, but...
Okay, thanks.
Thank you.
Thank you. Apologies, but it's such you are very passionate in the discussion. But yes, we will need this also for the future seminars.
That's about my tea.
Okay. And the next question was by Virna. Virna, can you please come?
My question
He took
about the minimum.
Okay. So he stole your question. Good for you. But this means that the question was obviously important. And then Sylvia had a question.
Yes.
I don't know from where to start. I'm experimentalist, so I will not ask. I will ask questions which concern for experimentalists how to calculate real system. So first I would like to ask you this software you use to calculate, I guess, to find the ground state or state with minimum energy for some system.
Yes.
Can you say?
I use quantum expression because it is free.
No,
it's
but
open source.
what is the real system compound? What was it? A layer or what?
It says KC8.
So this is
Graphene with the calcium inside.
okay. So this is one layer thing or
One layer thing.
One layer.
One layer thing. Yes.
This is the only what you tried until now.
No. For now, I just calculate this. So I'm consulting with my mentor. What to do next? Right now, we're in the phase of calculating this pure KC8 stuff.
And this gave a reasonable ground state or state with minimum energy. You experimentalists expect. I mean, experiments show. This is my question.
No, the thing is that it's still in some kind of trial state. So we do calculations, and then I just see the results, and I said, this one is big, try again. This one is minimum. This one is minimum. This one is minimum. This one is minimum. And after many tries, that's it.
Okay, if I understand well, the most important thing in DFT is the choice of exchange correlation functional.
Yes.
Which depends on different programs and pseudo potentials.
Yes,
which is also not straightforward.
Yes, it is. It's approximation.
So I wonder how are you going to choose? My first question: how are you going to choose these two of them? I mean, in comparison to a real system, because you said that you would like to get closer experimental theorists. You are going to study. You see what I mean?
Yes, I do. The thing for now, those pseudo potentials. Wait, just to give this the definition here. What was the most important for me right now? That they are normalizable. So the integral of all calculations or probability equals 1. Some pseudo potentials are not normalizable. Some are so strange that are only for some experimental calculation that you want to see how it will behave. Maybe. So the most important thing here is that they are normalizable.
Okay.
What is the concern of me? I use this.
You want this? Just please be tender.
Oh, it's sharp. But yes, and
because I guess you I guess you are going to use this program more or less all the time. So
yes.
You have to choose. Then you have functional discorrelation exchange functional right defined because there is.
Yes, I heard from. Well,
yeah.
Look here.
But let's keep this. Let me ask to me the more important question. In your calculations,
Yeah.
do you relax only atomic positions, or you relax at the same time crystallographic parameters. See what
No,
I
no,
mean?
I know. There is that VC at the end. Parameter. No, I just.
Or you just take
No, just point positions. What I relax.
only.
Yes.
And not. So you have from X-ray, I guess. You have crystallographic parameters. So if it's 2D, you have.
No. This stick as a constant.
This is constant.
Yes.
Okay, so this cannot vary. I mean.
No, I don't vary them. There is a possibility to vary those, but I have to keep them as a constant.
As far as I know, okay, no, I work with more crystalline materials, and for DFT, if I understand well, it's very important to relax both crystallographic parameters and atomic positions. Otherwise, it's DFT. Some people who are very strong in DFT would say that this is not a correct calculation. I know that, for instance, for materials I have studied and used, okay, I didn't make calculations, but I interacted with theorists doing that. It was important to do both, to relax also crystallographic parameters. But the problem is, if it's, this is why I asked the question, do you have one layer or have more layers?
No, one
okay,
layer.
let me just, so if you have more layers, then these van der Waals courses are important. And in most programs, I guess also in this one, van der Waals is not inside, within the program.
No, it's not.
This is why, this is why people fix crystallographic parameters and relax SU atomic positions, instead relax in both. So I think all this is important. So if once you go to real materials and maybe more lattices, because two-dimensional materials have not only one layer. I mean, today it's more interesting even to go to several layers. Then without van der Waals, it would be difficult. So this is what I wanted to ask you, but you are at the beginning, so I know, but just keep in mind.
Thank you for your comment.
Thank you, Silvia. There were two more questions so far. Next is Željko Rapljenović, please.
Maybe he's ready for me. This is sharp, so come, give me.
Can you just use the laser pointer then?
In his eyes. Come.
So, just a quick question following on Antonius. Is there any meaning, physical meaning, to the local minimums you find in
Yes.
this?
Here are the theorems.
But the local minimum, not the global
I
minimum.
know, as much as I know, there's just a mistake that the procedure does.
Sure.
That's if it would have meaning, I wouldn't just reset, restart it, and search for a real minimum.
Okay, so you are happy, Željko, with the answer. And then one more question was by Zdravko. So here is the microphone, wherever you speak. Around here is fine. You
It is
can
your
also use the blackboard.
introduction
if you want.
to this. No, not this introduction, but the whole thing you have done is the introduction. And in fact, I would like to know what is the reason why you do that. What would you like to do based on this local density function theory? Because I'm not familiar with this computer program, but at the end, I'm sure this program was used for several things, and you can know how well they are approximated using this computer.
Yes.
And then you apply this to several things, but I would like to know the reason. What would you like to do later on based on this solution, which is, or you have said is more or less known?
I know, but the thing is, what I really want to do later is to calculate plasmonics using using this. I get basic style. That's the theory like those. Sorry, my brain stopped working. All the start the calculation that function theory non-consistent calculation gives us out. And after that, in this system, put it on some substrate later, and I'm not sure still which one or what. And then I would like to see plasmonics in all of the system here.
Search for harmonics.
Yes.
Okay, because it is the seminar when you have to explain to the audience what is the general form, what would you like to find out in your doctoral study.
No, I thought that this seminar can be any area, anything that is related to my work. So what I planned to do was a theoretical description.
Yes,
of the
okay,
algorithm.
wait.
That was the idea, basically.
Just I would like to know, I think all of us would like to know why you have done these calculations, because this is just a standard application of this functional theory, but as you said, this is just a starting point for something else.
Yes.
And
I said,
maybe
right now,
you can just tell us a few more things, what is going on using this functional theory, what you really want to achieve using this standard method. Later on, you have plasmonic or what?
as I said, everything is still at the beginning, everything in my head. I'm just considering, okay, plasmonic, what I want to do. But now, it be just KCA on, right now I think, or SO2 substrate. Will it be, or right now SO2 seems like a reasonable thing.
Okay.
And, or what, just everything is still in my head, not so clear. So I am still thinking, should I do this, or should I do that, or it's still in my head. But KCA will be the system I will observe.
Okay.
That's it.
Okay, thank you.
Thank you.
And there was one more question by Predrag. Any more
Now,
questions?
stole the question from me, but I have another one. Okay. So it's purely theoretical, I mean, generic question. So you want to study some type of the systems, you said that Pauli exclusion principle is very important, and then you want to apply it to the two-dimensional physics, let's say, solid state system. So in 2 dimensions, there are some particularities which does not exist in 3 dimensions. Do you know what are those, and why it is not important for your type of the study?
The thing is that, as I might guess, is that in 2 dimensions, there are no interactions with other layers.
I mean,
Very
very generically about statistics. When we speak about statistics of particles, there is something particular in 2-dimensional. If you have effectively 2-dimensional systems, then you have effective degrees of freedom. Okay, then you have some strongly bounded electrons or what, and then you study effective degrees of freedom. And then these effective degrees of freedom can have a different statistics in general. It doesn't have to be Pauli or
the important is that we do with
Einstein or
Fermi statistics. We do with those commutators. That's the only what's important
but
here.
in 2 dimensions, you can have something else. Generic. Oh, yes. You have exotic statistics in 2 dimensions. You can have anyons in 2 dimensions. So you can have something which doesn't respect both Einstein and Fermi statistics. And now, do you understand why it is not present here? Your case, even if you are looking at this as a 2-dimensional system.
Can you tell me?
Well, I mean, I guess, because from what I understand, I mean, basically your system is 3-dimensional. I mean, your electrons keep their identity. It is simply you are looking at it from the 3-dimensional perspective in the sense that it is
but those points are
inside of 3 and not the 2-dimensional, really 2-dimensional effective system. It's the difference. So your electrons keep their let me say identity.
Like in the real world.
Like in the real world. Okay, it's not, but it is important, that you understand that when you are doing 2-dimensional theoretical physics, I mean that there's something else which can exist, which doesn't exist in 3 dimensions.
Well, there is time to understand these things, and I just started to do this.
Okay, thanks.
Some online questions?
Not online, as far as I know, and also not anybody from this audience.
I have a question.
So what more, Antonio, can you please come?
Just how long does it take typically for one calculation from start to finish?
The thing is that you can do, there is a possibility to calculate on multiple processors.
Okay.
So in my computer at the institute, it has 12 cores. So it can be done pretty fast. For example, on 4-core processors, to do self-consistent calculation for this KCM, it takes around 8 till 10 minutes. And not that non-consistent calculation, because self-consistent calculation it takes around 2 to 3 minutes. And if I do it on my 12-core processors, it can be done in a minute, and non-consistent calculation can be done in 3 to 4 minutes.
Okay.
So it's not accelerated linearly compared to the number of processors, but it is faster, really.
Okay. Thanks.
That's it.
In case there are no more questions, I would like to thank Josip for his talk and to all of you for the discussion. Hello, we are back and now heading for our last seminar in this year's session. And I also welcome RIJEKA Jordana, who came now for this seminar. And right now I clarified about the connection, so some of you were able to connect immediately, and there is just a different link. But if you go to YouTube channel of department, you are directly headed to also to this broadcasting. And thank you for your feedbacks. Some of you wrote me mails that you can hear well, see well, also the questions, so we will just continue as we started. The next seminar, the last one, is by Luka Sinković. He is also working in the field of condensed matter physics, and his mentor is Ivan Balog, and he will speak about bridging the gap between renormalization group and numerical calculations. Also, for all questions, you can send them to my email if you are following online, and then they will be asked to Luka after the end of the talk. Thank you, Luka. Please, you can start your presentation.
Thank you, Professor Dijana. Hello, everybody. My name is Luka Sinković. I work on the Institute of Physics, and today I will be talking about bridging the gap between renormalization group calculations and numerical calculations. If this title is confusing enough, the next picture. I'm sorry for inconvenience, but oops, okay. This is the brief picture of what I will be talking about. I will be talking about working with Ising model and its other version model with random field. So let's go through some outline of the seminar. First, let's cover some theoretical background for phase transitions, some critical exponents. Then we will make some insight into Ising model and random Ising model. Then we want to discuss what are the main differences between the renormalization group and numerical calculations, simulations. Then we will look into finite size scaling and see what it allows us to do. This idea of the seminar is to grasp an idea of the course, which will my work during the doctorate studies look like. So we will take some look to the present work of mine and to some planned future work. Then we can conclude the talk, and we'll have some time for discussion. As was seen on the first picture, we will be talking about phase transitions, and we can take ferromagnet as an example. So below, phase transition happens at some critical temperature, and it is denoted by some measured quantities. They have mathematical divergence, but in real systems of finite size, of lattices of finite size, we don't have strict mathematical divergence, but we have something like this. We have some peaked quantities, not strict divergence. To comment on a picture before, I mean, we can see it here. For critical temperature, system goes through phase transition. For low enough temperature, system is in state of order, and for high temperatures, system is disordered. So let's talk about some critical exponents. Phase transition is noted by all important quantities. They have divergence, and they show some power law behaviors. We can see some quantities here. For example, correlation length that has exponent ni. Exponent appears on the reduced temperature. We have magnetization with exponent beta, susceptibility with exponent gamma, heat capacity with exponent alpha, and we will observe this on Ising model. Ising model is the simplest mathematical model of ferromagnetism. It was proposed by Wilhelm Lenz in 1920, who gave it as a task to his understudy Ernst Ising, who solved a one-dimensional problem in 1924. Lars Onsager solved a two-dimensional problem in 1944. With two-dimensional problem was a bit tougher case than one-dimensional. So let's take a look at Hamiltonian of the Ising model. We have sum over this is a constant of interactions. Sum goes over all nearest neighbors in the system, and goes only once. We don't count yacht and I and yacht. And it has some homogeneous magnetic field that is being applied to every node in the lattice. The system is determined by complete microscopic picture of the system is configuration of spins. So if we want to calculate a partition function, we must sum over all microscopic states of the system. Then we can go and obtain free energy of the system, and from free energy we can get some further. But let's take a look first on random field Ising model and how different it is to pure Ising model. Random field Ising model was proposed by Imre and Ma in 1975, and in a sense it is really similar to pure Ising model, but it has this sum which includes random field. Ising model had this homogeneous field in its Hamiltonian, but random field Ising model has this random field, which is obtained by rolling the dice and for each node, and to take values from Gaussian. We can non-trivially complicate this model even further if we allow long-range interactions. So if you imagine nearest neighbors, one-dimensional system would have two nearest neighbors, two-dimensional system would have four nearest neighbors, three-dimensional 6, and so on. But here we introduce long-range interactions. They enter as additional factor with dimensionality into this constant of interactions. So we can call it an effective dimension of a system. What we will be doing in numerical calculations, we will be trying to calculate the ground state of the system of random field Ising model, because its critical behavior is completely determined by the ground state.
Sorry. Maybe you can be here in front of the camera so people can see you.
We have a
because here nobody can see you, and they can also hear you better. So
okay. We had some problems with PDF document, so.
But you can see.
Okay.
So,
yeah, sure.
So here in front of this blackboard, you are visible to the camera. Here not.
Okay.
Sorry for not mentioning your
Yeah, no problem. Thanks. Let's take a look at the random field Ising model a bit further. We can see its phase diagram and transition between paramagnetic phase and ferromagnetic phase happens over this line. So if we take a look at the fixed points, this is a fixed point for pure Ising model. Fixed point for random field Ising model is not on the temperature scale, but on on disorder scale. So we have to be very careful because temperature is here basically irrelevant. We will somehow probe the system over the disorder. So okay, what I also wanted to talk about is short-range interactions versus long-range interactions. For short-range interactions, we have a range of dimensionalities between 2 and 6, where below lower critical dimension of the system, we don't have a phase transition anymore. And after the upper critical dimension, we have mean field. Gauss theory describes the system well. So what happens in the range between 2 and 6 for random field Ising model is not trivial. For long-range interactions, we have this additional variable sigma that enters along with dimensionality. So it is kind of connected with lower and upper critical dimensions. Yes, something.
Oh, well. Can you maybe use the keyboard to change the
Okay.
slides?
Okay, it's good.
If the battery is out, you can also use the stick. There's a pointer
Okay.
and keyboard to change the slides.
We have a critical exponent. We can take a look at critical exponents in random field Ising model. We have two different correlation functions. One is called connected, the other one disconnected, and they have two different critical exponents, eta and eta bar. Critical exponent ni enters over correlation length, like in the pure Ising model. Some experimental realizations of random field Ising model are as stated in the works of Birgenau, and this is some sort of aerogel. It is a porous compound that is solid only 2%. And when it is wetted, there is a liquid-gas transition that acts like a random field Ising model. What is the main idea of this talk? But also of my work, to bridge a gap between language of the renormalization group and numerical simulations. Those two approaches are two general frameworks for studying phase transitions. In renormalization group, let's take a look how different they are. In renormalization group, we start from Hamiltonian, and we want to get effective Hamiltonian by successfully integrating out degrees of freedom from those with short wavelengths to longer wavelengths. those are effective couplings. At the end, we want to get some sort of effective potential. We also can obtain critical exponents by this method. Numerical simulations are more straightforward. We have the model. We take its microscopic Hamiltonian, as shown before, and we simulate the systems of some finite size L. Phase transitions are possible to observe in infinite systems. So we, in numerical simulations, we expect to get something as shown on the beginning of the talk, not complete mathematical divergence, but some peaked peaked functions. We will here obtain scaling functions of these observables, and critical exponents will be obtained by collapsing data for different L sizes. It is clear that there is a language barrier between them. They have different angles on viewing the same thing. What allows us to what will allow us to in numerical simulations obtain these scaling functions is hypothesis of homogeneity of free energy, and it says that free energy has its analytical part and singular part, and that the rescaling of the singular part goes with this scaling number b. For this case, we have relevant variables of scaling, which is tau and h, and those are relevant variables for Purism model. All other variables are irrelevant. So by combining the derivatives and second derivatives of free energy and rescaling the system for B for correlational length, we will get relations for exponents. What is shown is that exponents have some properties that they are not one would think they are independent of each other, but they're not. There are some identities that connect them. So we can take a look at finite size scaling. So let's take an example with susceptibility, which is a measurable quantity, and what we get if we simulate the system for different L sizes is shown in this graph. And susceptibility scales by this term. So what that means is this. For 3D e-sync, this exponent is of range, I think, 2.5. For 3D e-sync, this exponent is 1.5. So if we increase L by simulating for greater and greater lattices, we can see that this here will have greater rise in value. So the area around 0 is kind of being pushed together. We will the critical exponents will then be determined by collapse of the curves. We can also take a look at Binder cumulant, which is a nice variable because it does not scale. It has only one. It has only one exponent that is not 0. So we can see. I mean, what we do here is we take curves and we will get scaling functions by knowing these crossing points of the curves of the cumulant. Scaling functions versus renormalization group. In renormalization group, what we get is this kind of some effective functions which determine effective Hamiltonian. How to connect those functions to scaling functions that we get from the numerical simulations? We can take pure Ising model. We will determine the probability of fluctuations of magnetizations. We will do that for different lattice sizes, and at the very end, collapse will give us scaling function of this probability, and it will be as stated here, where x is the this in the brackets. What we can observe on the graph here, there is data for two different sizes of L. This is scaled data. So on axis we have this already scaling function. And this is really great because what we find is that effective potential that is obtained from renormalization group. This is this red line here. Is completely described also by this probability with the scaled function that we obtain, and with violet dots, we can see that what we get from the numerical simulations responds well with renormalization group predictions. So this is some fresh present work of mine. Not the renormalization group. We here use existing predictions, but the aim is to establish the full correspondence for any renormalization group quantity. Then we can tackle some bigger questions. We have a problem, a famous puzzle by Parisi and Sorlus from '79, which is called dimensional reduction. So the claim is that dimensional reduction connects pure Ising model with random field Ising model by stating that d-dimensional random field Ising model is completely equivalent in critical behavior to d-2 dimensional pure Ising model. So that was a proposition from '79, and what was thought then that lower critical dimension of random field Ising model was 3. So when it was found that in '89 that the lower dimension of random field Ising model is 2, it was stated, I mean, it was clear that dimensional reduction does not stand anymore, because we know that lower critical dimension of pure Ising model is 1. For upper critical dimensions, dimensional reduction stands, but for lower critical dimensions, it does not stand. We have here dimensionality of Ising and random field Ising model. So yes, for upper critical dimensions, dimensional reduction stands. For lower, it does not stand anymore. So a good question is how does dimensional reduction break? The scenario was proposed recently in 2013. That dimensional reduction breaks because of dominance of avalanches on the critical behavior, and it was calculated that it breaks somewhere around 5.1. And we call this dimension dr where it breaks. So what we want to achieve, and this is theoretical data, which implies that there is a loss of it can be seen, but this is some quadratic behavior over the 5.1, but for blue lines it becomes more and more linear. So we have the singularity. This is not not analytical anymore. So what we want to numerically achieve is compare that analytical prediction, and we want to simulate and find this cusp singularity. For random field Ising model, we would have to go to the sizes of between 5 and 6 dimensions. Here, one-dimensional long-range Ising model comes to rescue. In 2014, it was also proposed that for one-dimensional long-range random field Ising model, there is a similar scenario as in random field Ising model. It is connected with sigmas, with a range of interactions, and it was proposed that the number is right here, 0.379. One-dimensional long-range Ising model is way cheaper to simulate, and we will try to obtain this result in this model. If this test is positive, that is a strong argument that this scenario will also happen in the original model. And at the end, let's conclude some points from this second part of the seminar. We described Ising and random field Ising models. We actually saw that there is a language barrier between renormalization group and numerical simulations. Scaling functions that are obtained through simulating are different to those functions that renormalization group uses, where we talk about effective potentials. We need to do careful comparison of these two approaches, as we don't want to lose some of important physics in the process. And after this correspondence is done on the normal pure Ising model, we tackle the dimensional reduction problem. One-dimensional long-range random field Ising will then be used to simulate and check this scenario for cusp singularity. And this is the end of my presentation. Thank you very much.
Thank you, Luka, for this clear and well-structured presentation. I would like to open a discussion. Željko, Silvia, Virna, Antonio, Predrag. So, Željko, you can come please for the first question.
Can you put the slide 13?
This one?
Yeah, what is this? X.
Yeah, tau.
Tau.
It's temperature.
Okay, so the phase, the L is the size of the system.
Yes.
Okay, and are these peaks on the same temperature?
So no.
No.
I mean,
They're on a similar, but yes.
Yeah.
Nice. Thank you.
Sylvia?
Well, stop talking.
Well, if you don't mind. Or you can yell and then they will hear you.
Okay, well, I'm quite lost in simply because, okay, this is very specific, I would dare to say, narrow research field in solid state physics, but I catched two words or concepts which are quite hot and very important in condensed matter. And this is criticality and disorder. So first, please, can you explain what do you mean by criticality?
By criticality, I mean to watch. I mean, take a look at the system in the vicinity of the phase transition.
What kind of phase transition?
Here we talk about
Because, okay, I mean, it's obvious from all what you said, but I think I missed that you say quantum phase transition, because there are also magnetism can be in classical range. So when you speak about criticality, then I guess you mean about quantum phase transition. So where quantum phase transition from paramagnet to ferromagnet, what you said at the beginning, I think, when it happens?
This is, I guess, if I understand your question well, this is like a classical model.
This is classical, but you
Yeah, and
you have critical behavior, really? Okay, I don't know. I'm asking.
we
So all this is classical story.
yeah we don't have.
So what when you you said one slide you said temperature is dangerously irrelevant. I didn't understand this.
Temperature is dangerous.
Does temperature play any role in your story?
It enters into scaling relations because I mean it goes into zero because if you take a look at this fixed point, it is not on the temperature axis. So if we go to the critical point, to the fixed point of random field Ising model, we take a direction of lowering the temperature. So what is dangerously irrelevant in temperature is that temperature goes to zero, but it enters the scaling relations over the exponent of theta, and it does some stuff into scaling variables. But it is irrelevant as the exponent in the beginning of the system analysis.
Okay. Just to try to relate with reality. So this, you mentioned at the beginning two systems, two materials, if I remember well. One of the first slides, you had formulas of two materials. You remember?
You mean those experimental?
Yes.
Okay.
Yes. Yeah. Okay, so I guess that your calculations, using renormalization group or numerical simulations, have they been done on this material for physics of behavior of these materials? So I wonder what is explained and what is open, what then your calculations can put more light on that.
Well,
not only your calculations, but calculations of people in general in this field.
Okay, I'm not that well equipped with this experimental realizations of the model. I'm just stating it that it has been done experimentally. It's not only numerics, but numerics here very well describe what happens in reality, because it is pretty straightforward. If we begin from the microscopic Hamiltonian, we work on some lattices that have a finite size, and we get the similar results as experimental, as those that are obtained experimentally. So.
So these systems have phase transition, I guess, between paramagnet and ferromagnet, or is that so?
This aerogel.
I'm asking. I don't know.
It's liquid gas, but those are.
Okay, maybe just it'll be good that you in the future you can show a little bit of
Okay.
behavior. You see what is measured, and then that experimentalists, as myself or the others, could easier get the essence, the meaning, the purpose of your
Okay.
calculations. Of course, in physics there is always large relativism, or physics for the physics sake. But we try, as Josip said in his talk before, it's nice to try to have some connection between calculations and real systems. If I can, just to mention another thing or concept is disorder you mentioned.
Mm-hmm.
So does that mean that your Ising chains or whatever, they contain some disorder, or they are clean system? When you say for experimentalist disorder, I immediately think about something which disrupts order along the chains, etc. What do you mean by disorder?
Disorder enters here from the random field.
Random.
Yeah, because we have we roll dice for every node, and we apply different magnitude of field. So, sorry?
External field.
Yes, and we end up with a configuration of disorder, and we want to have a big number of those configurations because we can obtain better results with having bigger configuration numbers for.
Thank you, Selena. I think next question was by Vilma. This time it was not stolen, or
Yes.
again?
I was meaning to ask you why the temperature is dangerously irrelevant, but I got my answer, so.
So no more questions. Okay, Antonio, please.
Okay. So, since we're on this slide, I'll ask you first. So, yeah, it's about on the same topic of temperature being dangerously irrelevant. But I think so. Temperature itself, I mean, as a parameter, is irrelevant. But the temperature as a physical parameter should still hide somewhere.
Yeah.
So
that I mean it enters into scaling relations.
yeah, but where does it enter? Is it through this disorder parameter, or I mean, I didn't quite catch.
Yeah. It enters. Sorry about this. Yeah, it enters into those for have this identities for exponents.
Yes.
So temperature enters through this homogeneity and have the exponent theta, and I mean we lose it in random field Ising model because it enters as a third exponent. So it's irrelevant because it goes into zero, but it's relevant for the other exponents.
And another thing for the random field Ising model itself, for the Hamiltonian. So I mean, it's an interesting thing. I've never really seen random field Ising before. So the extra factor that you add up, the random factor, is there a kind of a reason or motivation why it's sampled from Gaussian distribution, or is it just the model stated like that? And
I guess that's true. I mean, it's we want to have this random complement in it.
But I mean, it could have been sampled from uniform distribution, from minus delta 0 to plus. But yeah, I guess it's probably just, quantum mechanics stated like that.
Yeah.
Okay, cool. And just to get back to this critical.
Okay.
So I noticed that the breakdown dimension is like not weird fractal, not whole number dimension. Is it possible to do numeric simulation with non-whole number dimensions?
That's the problem, I guess.
Yeah.
Because random field, simulations are as complicated as you have number of dimensions. Going into dimension 5.1 is really tough even for a computer.
Yeah.
So one-dimensional long-range Ising model, which has effective dimensionality and can reproduce this range of non-trivial behavior of the model, but it can do so in lower dimensions. So it's easier to compute.
Okay, I can see that. Makes sense. Okay, thank you.
So far, there are no questions asked online, and there was one question by Predrag, and no other questions so far. So this is the question before last.
Well, it is not the one question, it's sort of a parallel question.
Okay.
Okay, first of all, Silvia asked this,
Can you come in the
but I didn't
frame?
got
It's from here, people can see you. Okay.
and it is about applications. I mean, this order parameter, what is physically is on these examples you wrote? It is not spin, probably, what we normally call spin, but it is something different. What is this order parameter?
It is.
It may differ probably from the system to system, but what it is.
It enters through the randomness of this model.
But this S, for example, S on the lattice point.
Okay.
I.
Spin.
Yes, spin. What does it represent in applications? Not mathematically. I mean, this sort of a mathematical model you can view it.
It can be
mathematically.
1 or -1.
Yes. So why? What are these degrees of freedom which you can model in this way? Of course, you can model spin if it is standard spin of the particle.
Okay.
But these are more complicated systems. Is it spin or is it something different? Is it orientation maybe of the molecule or something? Or what is this order parameter?
you mean in experimental?
Yes, experimental. On practical examples.
I'm not completely aware of that.
Okay, the next question is your title, in fact, renormalization group. You used it, but you haven't really explained. But do you know what is really the main point of the renormalization group and running couplings? Why it was introduced? What is so good about it? Why people use it so much?
I guess it can describe, it can give exact solution to some problems, but it is not so straightforward. You have to detect some mesoscopic degrees of freedom, and then integrate through these parts to get to the end. And this detection of these mesoscopic parts of the system is not so clear, so straightforward. So ingenuity is, I guess, in this.
There is some very simple. I mean, idea. That is how it started. In fact, okay, you integrate out something that you do not know anything about it, so you describe it by effective parameters.
Okay.
That is one idea. Then you have this important regime which now you want to model. But there is this, I mean, the question is the following. I mean, let's say that you have effective coupling. And then you can always fix it on some natural scale. For example, in quantum electrodynamics, it would be, I don't know, mass of the electron or something. You know, there is a natural scale for it. And you fix it to this natural scale. And you take this G, G0, and you calculate everything with this G0. You can do it. I mean, you do not need a normalization group to go. But what is so nice, I mean, about a normalization group when you want to study the properties of the system which are not on this, scale on which you define your coupling constant. Why? Let's, for example, to make it more simple for you, let's say, for example, that there is this scale on which G is much smaller than 1. So you can do perturbative expansion. That's fantastic, that's nice. And then you move from this scale, and you want to study system away from this scale. What is the good point about this idea of the renormalization group? That's the question.
Okay, that's not in my scope of understanding yet, I guess.
Well, when you use renormalization group, it's really something really, I mean, essential. I mean, because when you move from it and you calculate, some observable something, some quantity, what you are going to obtain are something which depends also on this ratio. Typically logarithms or powers of this ratio. So when you move, you can obtain some large quantity. If you move, let's say 10 by 10, I mean this is going to be 10. This is not small anymore. So now you have a small coupling constant but large thing, and you are not sure are the perturbative expansion correct. But if you use a renormalization group and you move from this scale to this scale, by integrating the renormalization group equation, it can happen that though this is large, this still can be small. And then you know that you can again apply perturbative expansion. It's very important. It is the essence of the renormalization group. This is really, something which. Okay. And the next question is, do you understand this scaling behavior on the critical points in which you have, these power laws? What symmetry is connected to this thing that you obtain power laws in the criticality? What symmetry in the system is usually? I mean, it doesn't come from the thin air. There is always a reason for something nice. That there are no exponential, factors or something. Which symmetry, scaling symmetry.
Okay.
So you know that there are these different types of behavior, that it's symmetry. That's important. And usually with scaling symmetry, there is conformal symmetry. That's the idea. You have it also in these Ising models, conformal models, which are describing critical points. Okay, this, I mean,
Okay, thank you.
Zdravko, did you have any question?
No.
Or anybody else? Okay, so far I always had questions for everybody, but I didn't ask them because either they were asked by somebody else or I wanted to keep the timing. But okay, I will just use the opportunity to ask you as last one a short question. You had very nice, I think it was on slide 6, nice graph, and can you just, okay,
Yes.
can you just explain it in more detail?
Well,
I would like to understand.
Well,
it.
it's the same thing as the graph on this slide. We have temperature axis, and for big enough temperature, system is in paramagnetic phase, in disordered phase, and for low enough temperature, system is ferromagnetic phase, and this is represented like this.
Okay, and TC? Is
Sorry,
TC?
TC is phase transition.
Okay. This is how I thought I understood, but I just
Yeah,
wanted
it's tilted.
to have more detailed explanation. And at the end, just to tell me what is your main motivation, your enthusiasm that brought you to this interesting field. This has many applications. You are doing theory, but what are the applications? What is the idea that you have behind your PhD work that you would like to do with this in
Well,
perspective?
I started working with Ivan from my master thesis, and we've already done this numerical calculations in one-dimensional long-range Ising model for critical exponents, and we want to observe and compare this to his present renormalization group exponents that are known. So, well, I guess it's this connection between two fields that is what is motivating me, I guess. And the simulation is kind of a big grasp because it's done on computer clusters with huge amount of data, and data analysis is another step that is big here. So I guess that's it.
So you will also learn to work with big data and analyze big data,
Yeah, maybe.
simulate, which is also interesting, and we will hear more from you also during this course.
Yes.
And not the course, but the whole studies, and also from all of you. Okay, Luka, thank you very much for your presentation and standing strong at the discussion, which was long. And to all of you who are present here, some of you, most of you for both days, to the audience who is following us remotely, and also to people who are not here but who are also helped a lot that this is organized and broadcasted and set up, to Marin Caruza, Marina Manganaro, Carlo Velichan, who has been here most of the time doing the techniques, and also Ljubo, who was doing all the organization and sanitary work, which is now required during the corona crisis situation. And especially I would like to add at the end that I'm very pleased that despite of this very challenging situation, when we didn't know until the very last moment how we are going to do these seminars, what are the rules. The rules were changing on the daily basis, that finally we all made it to be here, to have these seminars, that you have all shown your real dedication, and I think we can see it all as our common success, and that this will be a good start, also good preparation for the defenses of the fields of this generation. I hope that these seminars, even though your defenses will be different, but that they are going to be helpful to you to get prepared for the next defense, and also for those of you who are already our students since last year and are following, that this has also been useful to take part. I wish all of you who are not from RIJEKA safe trips to your homes, and hope to see you soon back for the defenses or for any other reason, because no matter where you are staying, you are always welcome to ask questions, to come here, to ask for a remote meeting, and I'm optimistic about our progress together. Thank you very much. Goodbye. A ja imam sada jedan sastanak sa nekima iz programa, posle toga da ćemo
A garanča je bilo 11.
A možemo i svi skupa.
Što nećemo biti vani. A mi smo napravili neku pozornicu i uz stolice na razmak i tako to možda u 9 ovako se ne pokvari ko što se kvari. Sretan put, vidimo se. Tehničke, to sam sad su to moje probleme, ali tako sam morala.
Ne, bio je da
Znači, ovo da i ove stvari.
što je s njima, moram vidjeti jer meni neugodno da sam morala gledati mailove, što inače ne radim za vrijeme seminara, da vođu na seminari tehnike, ali